Gravity. It's the force that holds us to the Earth, guides the Moon in its orbit, and binds galaxies together across unimaginable distances. It's a fundamental force of nature, woven into the very fabric of the cosmos. For centuries, our understanding of gravity was shaped by the brilliant mind of Isaac Newton. But in the early 20th century, Albert Einstein revolutionized our view of the universe with his groundbreaking theory of general relativity. Einstein's theory didn't just refine Newton's laws, it fundamentally changed how we understand gravity, revealing it not as a force acting across space, but as the curvature of space-time itself. Isaac Newton's law of universal gravitation, published in 1687, was a triumph of science. It stated that every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. This elegantly simple law explained the falling apple, the Moon's orbit, and the motions of the planets with remarkable accuracy. Newton's law remained essentially unchallenged for over 2 centuries, becoming a cornerstone of classical physics. However, as our understanding of the universe deepened, cracks began to appear in Newton's seemingly perfect theory. Astronomers observed slight anomalies in the orbit of Mercury that couldn't be explained by Newton's laws. Additionally, Newton's theory treated gravity as an instantaneous force acting at a distance, a concept that felt at odds with the emerging understanding of light and electromagnetism. Enter Albert Einstein. In 1905, he published his theory of special relativity, which revolutionized our understanding of space and time. Special relativity showed that space and time were not absolute, but were interwoven into a single 4-dimensional fabric called spacetime. This fabric was not merely a backdrop for events, but an active participant in the drama of the cosmos. Building upon special relativity, Einstein spent the next decade developing his masterpiece, the general theory of relativity. Published in 1915, general relativity provided a radical new explanation for gravity. Einstein proposed that gravity was not a force at all, but rather a consequence of the curvature of spacetime. Section 4. Warped spacetime gravity's true nature. Imagine a bowling ball placed on a trampoline. The ball's weight causes the trampoline's surface to curve downward. Now imagine rolling a marble across the trampoline. Instead of traveling in a straight line, the marble's path will curve as it follows the contours of the warped trampoline surface. This analogy, while imperfect, helps visualize Einstein's concept of gravity. Massive objects like stars and planets warp the fabric of spacetime around them. This curvature dictates the paths of objects moving through spacetime, just as the bowling ball's weight dictates the path of the marble on the trampoline. These paths, called geodesics, are not the result of a force, but rather the natural trajectories of objects through curved spacetime. Section 5. Einstein's equations, the language of gravity. At the heart of general relativity lie Einstein's field equations. These 10 interrelated equations, expressed in the language of tensor calculus, describe the relationship between the distribution of mass and energy and the curvature of spacetime. While the mathematics of general relativity is highly complex, the underlying concept is profound. Mass and energy tell spacetime how to curve, and curved spacetime tells mass and energy how to move. Think of the Sun. Its immense mass warps the spacetime around it, creating a gravitational well. Earth, following its geodesic through this warped spacetime, orbits the Sun not because of a mysterious force, but because it's following the natural curvature of spacetime created by the Sun's mass. Section 6. Proof in the cosmos. Evidence for general relativity. Einstein's theory, while elegant and revolutionary, needed observational evidence to support it, and evidence did come, validating general relativity in spectacular fashion. One of the first and most famous confirmations came in 1919 during a total solar eclipse. British astronomer Arthur Eddington observed that starlight passing near the Sun was slightly bent, precisely as predicted by general relativity. This bending was due to the Sun's gravity warping the path of the starlight. Another striking confirmation is gravitational time dilation. Einstein predicted that time slows down in stronger gravitational fields. This effect, though tiny, is measurable and has profound implications for technologies like GPS satellites. These satellites rely on extremely precise timekeeping to determine location. To account for the slower passage of time in orbit, corrections based on general relativity must be applied. Perhaps the most dramatic confirmation came in 2015 with the detection of gravitational waves by the Laser Interferometer Gravitational Wave Observatory, or LIGO. These ripples in spacetime, generated by cataclysmic events like the collision of black holes, were predicted by Einstein a century earlier. Their detection not only vindicated Einstein's theory, but opened a new window into the cosmos, allowing us to study the universe in a way never before imagined. Section 7. The Universe Unveiled: Black Holes, Cosmology, and Beyond. General relativity has profoundly impacted our understanding of the universe on the grandest scales. It's the cornerstone of modern cosmology, providing the framework for understanding the evolution of the universe from the Big Bang to the present day. It explains the existence of black holes, regions of space-time where gravity is so strong that nothing, not even light, can escape. However, despite its successes, general relativity is not the final word on gravity. One of the biggest challenges in modern physics is reconciling general relativity with quantum mechanics, the theory that governs the subatomic world. These two pillars of modern physics seem incompatible at their core, suggesting that a deeper, more fundamental theory is needed to unify them. Einstein's theory of general relativity stands as one of the greatest intellectual achievements in human history. It has revolutionized our understanding of gravity, space, and time, revealing a universe stranger and more wondrous than we ever imagined. Yet, it also reminds us that our journey of cosmic discovery is far from over. As we continue to probe the universe's deepest mysteries, we may find that even Einstein's mind-bending theory is just a stepping stone on the path to a deeper and even more profound understanding of the cosmos. The question remains, what other secrets does the fabric of space-time hold, waiting to be unveiled?